So this is called the discrete Fourier transform. And what is interesting about this is there's another way we can write this. If we notice certain things, if we look at this term, e to the I 2 pi over n, we can immediately see that it has certain very interesting properties. And that will take us back to our complex plane. Remember Euler's formula on the unit circle. So this will get us to the so-called nth roots of unity. That's what these things are. And omega sub n, they're called the nth roots of unity. And what they actually depict is the following. So this is our standard unit circle. Unit circle in the sense that this is 1. This here is it's complex plane, so this is I. This here is -1, and this here is minus I. Right? So this term we're calling omega sub n equals e to the I 2 pi over big N, where big N is the number of samples that we have. And these terms are referred to as the nth roots of unity. Why is that an nth root of unity? Unity meaning 1. Here you have, say, for some n, this is your theta equals e to the I 2 pi over n. And if regardless of what n is, if I have this, that number, what it means physically is the number of times you can go n times. You go n times, and you would have made your way around the circle, right? So if, for example, n was 1, that would give you e to the I 2 pi. We know that e to the I 2 pi equals 1. So you would do 1 and you'll be done. So that would be the nth root of unity. That would be the first root of unity. If instead n was 2, these 2's would cancel out and you would have e to the I pi, right? I pi. So pi, the angle pi is, this is pi over 2, that's pi. Pi will get you to -1, right? So if you had 2, if n was 2, that would be the second root of unity, meaning that you would go 1 and 2 and you'd be done. And going in these directions is simply, it's exponential. So it just means multiplying this root by itself, squaring it, so to speak. If n was 2 in the bottom and you squared that, you went twice, you would have gone all the way around the circle. If n was 3, it means you will go 3 times and you'll be done. If n was 100, this number would be smaller and you would go 100 times to get there. Meaning it is the nth root of unity. Meaning if you raise that number to the power n, you would always get 1. Let's write that out. The nth root of unity is a number denoted omega sub n equals e to the I 2 pi over n. And it has the behavior that omega to the n raised to the power of n equals to 1. So this is the discrete Fourier transform. What do you notice? Whenever you're multiplying things and you see a summation, there's typically a matrix vector multiplication in there somewhere. That's one thing to keep in mind throughout in math. And there is a matrix here. What's that matrix? Let's write it out. Let's draw it out. And then here, what are we multiplying by? We're multiplying here by f, by our samples. So f0, so this is a vector, column vector, f1, dot, 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 fn. So that's it. So the discrete Fourier transform is represented in matrix form as we've shown. The DFT matrix is a unitary matrix, and that's important.